Elizabeth Barnes is a professor of atmospheric science at Colorado State University. She has a Ph.D. from around here in Seattle in atmospheric science from the University of Washington, and spent a year as a NOAA Climate and Global Change Fellow at the Lamont-Doherty Earth Observatory. I had to look that up. It's in New York somewhere, right? Her research is largely focused on climate variability, predictability, and change, and the data analysis tools used to understand it. She's a founding member of the NSF AI Institute for Research and Trustworthy AI in Weather, Climate, and Coastal Oceanography, which is like all the keywords that matches stuff that happens at SciPy, which is perfect. I like it. Her current research topics include Earth system predictability, sub-seasonal to decadal prediction, climate intervention research, and data science methods for Earth system research. And her talk today will be Explainable AI for Climate Science, opening the black box to reveal planet Earth. So, welcome, Elizabeth.
Okay, thank you all for inviting me into your wonderful community. I have been here for 1 hour, and I love it already. So I am going to talk about work on explainable AI, or XAI, that we're doing in climate science. As Alex mentioned, I am trained as a climate scientist who now really has a foot in one camp of data science and still the other foot in my physical science, domain. So today, my hope is to convince you that there's lots of cool science to do in climate science, that there's a lot of applications of AI, but hopefully by the end, I'll also convince you that the explainability part of AI, the understanding how it's doing its learning and what it's learning, is, in my view, one of the most exciting reasons to be working in this area right now. So just the one little downer, I guess, maybe, to start off, climate change and environmental change, we have a really challenging future ahead for humanity, honestly. The Earth system is threatened. Humans are moving in the face of worsening climate hazards. And a big part, in my view, of my job is trying to help society anticipate what we can expect in the future years to decades. This includes both just understanding the climate that we live in today, as well as where it might be in the future. So here we get to machine learning or artificial intelligence for climate. And I want to be clear, in my view, I do not see this as the end-all be-all or it's solved all of our problem. It's just one of the tools in our toolbox. I teach a data science course for graduate students in our College of Engineering. And I always tell them, if you have 5 data points, please just fit a line, right? Please do not use AI, although they really want to so bad, okay? So I am not here to teach you to throw out the toolbox or to tell you to throw out the toolbox. All we need is a hammer. But I'm going to talk about the hammer and how we're using it today. So AI for climate is not new. Here are some older papers. And I will point out, I'm quite proud of this one for my field. 1964, if you look in the bottom right-hand corner, it's like a really, really simple neural network. And this was to do meteorological prediction. So there is a history here, but like many of the scientific fields, AI has really exploded as a tool in the past 5 years or so. And one of the things that makes our field so awesome and exciting is we have so much data. Now, it's not all good data, okay, and they all have their own issues, but we've been taking observations, people have been taking observations of the weather and the climate and the state of the ocean for hundreds and hundreds of years, writing it in notebooks, right? Ships taking sea surface temperature measurements since the 1700s that we have logs for. So we have lots of data. We have climate models. We have observations. We've been measuring Earth's atmosphere from space since 1979. We're starting to have a lot of data that we can use and play with and mine. And so I'm going to go through some big picture ideas of how machine learning is being used in our field, and then I'm going to focus on a few applications that me and my research team have been working on to give you a bit more of a flavor. So one big area is machine learning for post-processing data, things like data compression. Here's an example of predicting the errors of a weather forecast system to just try to improve that forecast after our dynamical models have made one. Another is what we call parameterization. So we want to improve our climate models. And climate models are trying to simulate the entire Earth. okay, and all of the things going on, down to the microscopic level, which they cannot do, just given the grid spacing. So what they do instead is we come up with parameterizations or simplified equations to try and represent cloud processes, the water droplets intersecting with other water droplets, for example. And machine learning is being used right now. It's considered a really exciting area to potentially help us do a better job at simulating these fine-scale structures. Another one, there's a cow. Didn't expect a cow today, I bet. This is one I don't think is terribly appreciated in my community, which is when we want to go to Earth system prediction, or I have colleagues who want to understand how much a dairy farm, how much milk they're going to produce in a season. And they know that the weather, how hot it is, how humid it is an important piece of this. This is really what data science, honestly, in my view, is all about, or data-driven science. It's going from the sun shining down, the winds blowing, all the way through the ecology, the biology, right? The physiology, to how much milk does that cow produce. And we cannot do that with Navier-Stokes and with all of the basic physics that we learn about, in class. And so I really think this is a huge, powerful place for machine learning to help us span that whole space. Another is merging observations and model data. I'm actually going to talk quite a bit about this today. The idea that we have so much data, specifically from climate models, but we have so little in general observations. And how do we merge them together to make the best predictions of the real world that we can? Another one is deep learning weather and climate emulators. And I'll mention this a bit more, but this is a big revolution in the last, I would say, 18 months in our field. People coming in and saying, replacing, I mentioned Navier-Stokes, throwing that out the window and completely replacing it with an AI emulator. And these tools are doing much better than anybody thought they would at this time. So this has been very exciting and stressful for some. Another is climate change communication. So the idea, we have a lot of science and numbers in our field, but how do we communicate what this means to the general public? And there have been many tools starting to be developed to show what your neighborhood or your house will look like on fire, underwater. Yeah, it's not pleasant, but here's an example. And then finally, to learn new things. And this is where I get really excited. We can be using machine learning to do not just our science faster, but to actually learn something we couldn't have learned before. And that will be a focus today. So in my group, our goal is to develop and implement AI tools to leverage imperfect climate models. They are wonderful, but the data we know is wrong, but it's really useful. How can we use AI in support of Earth system prediction across time and space? So again, climate models provide inaccurate, but invaluable parallel universes that we can mine for relationships. So my first example is going to be talking about how long do we have until critical warming thresholds are met. For example, you may have seen in the news things like 1.5 degrees or 2 degrees C above some pre-industrial level. Now these numbers are not some tipping point. It's not when we hit that number, all hell breaks loose, okay? But they are numbers that the international community have agreed upon as being sort of gates that they need to watch for. If we warm that much. But you will see there are question marks on the bottom of this plot. The big question is, when will we hit these temperature thresholds as a globe? And here's some examples of how we look at this. Each of the colored lines, these are time series, each of the colored lines is a different climate model. And the three separate panels show different scenarios of how the future may unfold, how emissions may change, whether we get our act together on the right, or whether on the left we sort of continue as we are now. And those dashed lines are different thresholds that I mentioned, 1.5, 2 degrees, et cetera. And what you'll see here is that while, yes, in all cases, the globe is getting hotter, you'll see those different colored lines. There's a lot of spread on when they cross those dashed lines. And this is uncertainty within our climate models due to how they simulate the Earth system. And so the big question is, which one's right, which one's wrong? Are they all wrong? Do we just take the average, which is actually what we've been doing for decades? We average them all and say, that's our best guess, all right? So what we did is instead, we trained a neural network to ingest annual mean temperature maps. So everybody think of 2023. I can show you a map of annual mean surface temperature. That's my input, that two-dimensional map, into a neural network. And we have it predict how many years until that climate model world hits 2 degrees Celsius. And we know this because we've simulated it already. Now in the observations, we don't know this, so we can't use observations for this training task. Now I sort of lied. We don't predict how many years. We actually predict the uncertainty associated with it. So we actually predict a 4-parameter distribution to allow us to have some uncertainty associated with that prediction. And if you want to see, people always are like, show me how good it is. Here's our testing results of the true number of years for our training set versus the predicted. It looks fine, but really this is not all that interesting because I already knew the answer because my climate model already was run. So this is actually a pretty boring result. The interesting part is now we say, now that we've trained this neural network to predict how many years we have given a map of temperatures, can we use observations and put those into that trained neural network and have it predict how many years we actually have in the real world? So again, these are actual observations of surface temperature in 1980, 1992, 2016, and 2021. These are not from a climate model. And we can use these maps and just perform inference with using these as our input. And when we do that, there's a few things. One, we cannot test if it's right because we don't know when that future will be. But we can still do some validation here. The first is for every map we have, we put it in and we have a prediction of how many years until we hit 2 degrees C. And this is that time series of those predictions. A few things I want to know. First of all, if the network's jumping around on its guesses, one year it thinks it's 50 years away and the next year it thinks it's 10, I'm not going to trust it. But what we see is this nice progression of 1 year closer every year, suggesting that the network has learned something useful in the climate models that is indeed applicable to the real world. Now, another thing you might note, you might be like, it's not super straight, there's a bump. Yes, I saw the bump too. All right, so this bump is actually really interesting. This is the eruption of Mount Pinatubo. And in fact, what happens when volcanoes erupt is they put aerosols up into the stratosphere and it cools the planet for about 2 to 5 years afterwards. So this cooling of the planet actually shows up in that surface temperature map, and the network thinks, oh, we're further away from 2 degrees than we were just a few years ago. So in this way, we're actually using our knowledge of the domain to validate and understand that maybe our network's actually doing the right thing for the right reasons. So in the end, we can actually make a plot with uncertainty of how many years until we hit 2 degrees based on these different climate forcing scenarios, the red being sort of the worst news, I guess, out of these three, and the blue being a net zero simulation. And what's interesting here is this particular approach finds a higher likelihood of reaching a 2 degrees C world, even if we do a lot more than we are right now, which is, I guess, I said I only had one depressing slide. Maybe this is the other one, okay? But I want to be clear, this does not rule out the possibility of us avoiding a 2 degrees C world. And what's different about our approach from the others of just averaging all of those predictions together, what's different here is we're actually using what the real world looks like today in 2023 and 2024 to make that prediction. Now, just quickly, I will note that was training only on climate model data, but I already told you climate models are imperfect. So one of the areas that I think our field really needs to work on is how do we still use some of the observations that we have? How do we wring out all the information that we can? So I showed you this approach, but we can also take another approach where we mostly train on climate model data, and then we take a little bit of observations when we've had it, because we have actually already warmed by 0.8 degrees, and we have already warmed by 1.0 degrees. And we just do fine-tuning of our network. In this case, this is for understanding what's happening over the central North America. And in that case, we see that our original network trained on climate models alone in the blue curve didn't really align well with the truth, but with that little bit of fine-tuning on the observations that we do have, we have a much better prediction consistent with what we've seen in the past and potentially a better prediction for our future. All right, I'm going to skip that one. It's giving something away. All right, so we've been talking about climate change and warming. This, if there's ever a slide to listen to in this whole 45 minutes, I would say it's the next two. So drink your coffee. All right. This is fascinating, and I think it makes the data that we play with every day so fun. All right. everybody hopefully knows at this point climate change is real and it's causing the Earth to warm. And here is a plot, many plots of the western US. These are linear trends, so these are the slopes of surface temperature from 2021 to 2050 in a single climate model. Okay? Now you'll see I have 100 of them up here. Where do those 100 come from? Here's what they did. They have millions and millions of lines of code for this dynamical climate model. This is based on Navier-Stokes, just your typical physics-based model. Okay? And what they did is when they ran the model, and then they reran it with everything else being identical, even on the same machines, which can be important, the exact same machine. But all they did is for the starting place, the initial conditions of surface temperature, they added a 10 to the minus 14 Kelvin bit of noise. And yes, I said 10 to the minus 14. Okay? This is tiny. And they hit go, and they ran it out. And then they did it again, and they added a different amount of noise at 10 to the minus 14 Kelvin, and they ran it again. These are those 100 runs and how their temperature trends look. Now, a few things to note. One, they're all red. Okay? That says climate change is real. It's getting hotter. Doesn't matter what your 10 to the minus 14 bit of noise was. Cool. But they're not identical, right? You see that? They're not the same exactly, and that's because of the butterfly effect, or the idea that small differences in initial conditions can lead to great differences in outcomes. Now, you might not be that impressed. You're like, but Libby, they're pretty much all red anyway. What's the difference? Let's look at a slightly shorter time scale of a trend. This is the trends in 2021 to 2030, so over a 10-year period. There are regions, or there are worlds or storylines where the entire western US is cooling, even though CO2 is still rising, aerosol loadings are still the same, et cetera. This is what we call natural or internal climate variability. And it is the noise that makes our jobs incredibly fascinating, at least for me, and it's not so much the noise, it's the signal I'm interested in. What it means is that this signal can confound our knowledge of what the near future holds. We can't just say every year will be hotter than the year before, because it's not true. All right, put another way, if you look at a time series instead, here's the same idea. Here are a time series of surface temperature, in this case over a grid point over Chicago. There are 100 gray lines on this plot. Each of those 100 is different only in that 10 to the minus 14 initial condition when the run was started in 1900. All right, we could average all of them together. Our community calls this the forced response. You average enough stuff, the noise cancels out, and you get the real signal. Okay, and what you see is this general warming trend, and this is what we talk about all the time. You might say, well, there are still bumps. Those bumps are actually all volcanoes going off. Even small volcanoes can show up in the global mean. All right, but if you just choose one gray line, like number 40, this could be the world we're living in. Or you could choose world 32, which is a different one, right? And shows different variability and ups and downs and swings of temperature over Chicago. And so what we're doing is using AI to leverage these models to constrain future projections, that is to understand those trends, which I just talked about. But we're also using it to make shorter term predictions. For example, if we lived in world number 32, would we have foreseen and predicted this cooling over Chicago over this 30-year period? And this is important for understanding and preparing for weather and climate hazards. Even on shorter time scales, it would be nice if we could predict whether it's going to rain in the next few weeks. And everybody probably laughs because they're like, you can't even tell me if it's going to rain today, right? We're working on it, okay? It's hard. And here's why it's hard. I give this talk and people go, oh, so climate prediction's easy, just do it. No, it's not, okay? It's really challenging. We cannot, and this is where I think many of the way we approach problems is different than many of our just pure AI colleagues. We don't expect to make perfect predictions all the time. In fact, that is not my goal. I actually think having that as your goal will lead you astray in this area. Instead, our goal is to look for specific states of the Earth system that lead to predictable behavior. We call these forecasts of opportunity or state-dependent predictability. That is, we need to identify when we can even make a prediction in the first place, which is different than let's just make good predictions all of the time. And this is where AI can help. So I like to think about it in 2 dimensions. Think of it as 80% of the climate data is just a bucket of noise that we have no hope. And just a little bit of the data, maybe 20%, falls along this beautiful line or this beautiful relationship. Our goal is to find that line amidst the cloud of noise. And what is one of these lines? Well, as 2 examples, the tropics, so where we all want to go on vacation, actually hold a lot of information about the weather that we're going to see in the coming days to months to years here, for example, in the mid-latitudes. For example, the Madden-Julian oscillation is this region of cloudy, stormy weather, this big blue-green blob that moves slowly across the tropics from west to east on approximately 30 to 60-day periods. What that means is when we see the storm in one part of the ocean, we know in a few weeks where it will be next. And because of that, like dropping a rock in a pond and it says ripples, this set of storms send ripples out into, say, North America, and it impacts the weather where we live. So we have some warning ahead of time. Also, you may have heard of El Nino and La Nina. This is an oceanic signal that also gives us predictability in the coming years. So farmers will actually, in the agricultural sector, will use this to understand whether it may be a bit more rainy or a bit dry. Okay, so how are we using this information? Here's an example. Let's say we're going to input sea surface temperatures over the past few years into our network, and we want to predict in the future, over the next 5 years, will it be warmer, average, or cooler than normal? Seems like a reasonable kind of task, although it's hard to do. So few things. First of all, we need data to do this. Machine learning is super data hungry. We cannot use observations for 5-year predictions. We only have about 40 years. We have about 10 observations, 10 data points to deal with. So instead we use climate model output. This is trained on 3,630 years of data. Okay, now we're talking. And when you look at our overall accuracy, I'll remind you this is a 3-class problem, and we made it so it's balanced. What that means is random chance is about 33%. For those of you in the back, you don't have to squint too hard to see that looks pretty much like 33%. That's pretty dismal, all right? But instead, if we focus on when the network is confident in its predictions as a form of uncertainty, and we only focus on when the network thinks it will be good in the first place, this idea of this forecast of opportunity, we start to see skill pop out. And when we really look at the network's most confident predictions, we see our accuracy go up substantially. That is, we need to be training networks that know when they know and know when they don't know, and really only focus on when it's confident. Now, this is for climate model predicting a climate model, which at the end of the day is not where we live. We live in the observations, or in the real world. So this is that same network, but we put in observations now. And again, if you just looked at all of the predictions, this would be very sad, and you might as well have said this was a failed experiment. But if you look at when the network is confident in its predictions on the far right, you see there are locations and times when we know that we're going to be right. And I think this is where AI has really allowed our field to excel. We didn't have methods to do this and identify these states otherwise. But how is the network making its prediction? All right, so what we want to do is we want to open the black box with explainable AI. All right, we want to understand how it's making its prediction because maybe we can learn something about the climate system and how it works. There are quite a few papers now. I mean, there are papers coming out from computer science every day with a new explainable AI tool. And this has been really hard for my community to ingest because it's written in computer science language, and we need a translator. But now we're starting to have papers that fit that. So for those of you not familiar, I want to give you a quick idea here. Many attribution methods in XAI work like this. Let's say you have an image of a cat and you push it through your network and it predicts a probability of 80% that the cat's in the image. And you say, why did you predict that? Where did this 0.8 come from? Well, many of these methods will then take that value and somehow propagate that 0.8 back through the network and give you a heat map showing you the regions of the input most relevant for that 0.8 prediction. Some are even conservative, where if you add up all those pixel values in that heat map, you'll get 0.8. Okay, so the idea is here you're underwhelming. It's a cat. It looked where the cat was. Not that exciting. Fine. Let's do another one. So here are pictures of horses, and we want to know is there a horse in the image? The network got it right, by the way. Good job, network. And we say, how did you know it was a horse? Let's use explainable AI and make heat maps. So here are some of those heat maps, and sorry for the colors, but the red shows the regions that the network used that were most relevant to determine there was a horse in the image. And if you sort of squint, maybe I can convince you at least for one of them, they align with where horses are, right? Okay, fine. Let's do another one. 3 horses in the image. Network got them all right. Yes, there are horses in this image. Where was the network looking? What regions were most relevant? Who sees it? In this case, it has nothing to do with the horses. It's in the bottom left-hand corner. There's a copyright symbol. And the training data for this network, when it scraped the web, took almost all of the horse images from the same German website with this copyright image. Now, some of you might say, yeah, but it got it right. But I think most of you would agree that this doesn't feel right. We want the right answers for the right reasons. And if I owned a horse and I put my photo of a horse in this network, I would want it to be able to tell me there was a horse. And in this case, it wouldn't be able to, right? So this does not bode well, especially with physical scientists. They do not like this. Actually, I've had people say, now that I've seen your talk, I'm never using AI again. Not the point, but okay. All right, so why should you care about explainable AI? In science, our ultimate goal is just to ask why all of the time. But even if you don't care about why, you should still care about explainable AI. First, it helps you gauge trust in the network that you're using, especially for high-stakes decisions. 2, it helps you fine-tune and optimize your network to do what you think it should be doing, but also be flexible enough. And finally, again, to learn new things you didn't know before. Let me give you an example. But first, I want to put in this disclaimer. Yes, our ultimate goal is to learn causality. And yes, I'm aware correlation does not equal causation. But I do think explainable AI is a step in the right direction. So here's a similar task to what I showed already. We're putting in maps of sea surface temperatures to predict land temperature in the coming 5 years. We call this a multi-year prediction problem. Once the network makes that prediction and it does an okay job, we can then say, how did you make that prediction? What did you use in the inputs to make an accurate prediction of the climate in the coming years? And we can get heat maps now. Now, this is not a cat anymore. These are heat maps of the oceans and the regions of the ocean that were most relevant for the network to make its prediction. And we see that depending on where the network is making its prediction for, it uses information from different parts of the ocean circulation. And these regions are well known as important locations for prediction, but it was unknown how to make use of them. Furthermore, what makes AI so great is the nonlinearity. For the same location, so this is always predicting for the west coast of the US, you can have different sources of predictability depending on what's going on in the world, in the climate. And this is something, once again, linear methods cannot do. All right, so that's on these multi-year timescales. What about the weekly timescales? So can we predict, in a few weeks, we're going to have what they call an atmospheric river hit the west coast, dump a bunch of rain, and maybe we're going to have an issue with our reservoirs, right? Reservoir failure. So reservoir managers need to know, should I let the water out now, or is it going to be dry? Should I wait? And once again, we can use machine learning. What we do is we'll input maps of the tropics where we know information about the coming weeks is held. And we use that as input to predict what will the circulation or the winds or the rains or the temperatures look like over the US in the coming weeks, in this case, 3 weeks later. So we can do this within a climate model. In this case, we are using 800 years of daily data. Again, if we wanted 800 years of daily data from the observations, we've got about 700 more years to wait. Okay, so climate models here are a wonderful tool. And we can make these predictions, but we can now start to play games where we train on data from the present day climate in our climate models, but we can also now train on data from the future, right? From, say, 2100, because we can run our climate models that far. And when we do that, we find that on the surface, it doesn't look like our ability to predict the weather changes much. But if you look at those special predictable states, as shown on the far right here, we see that in the future in this scenario, the West Coast weather becomes less predictable than it is today. This is something we could not have even asked or answered without AI and our climate models joining teams together. Furthermore, we can say, but why are they changing? right? We're all really skeptical. And we can actually, once again, make heat maps and understand that it's actually the changing of El Nino in a warmer world that causes this change in skill. All right, so I started off talking about this coupling between humanity and climate hazards, and this is really complex. And human development based on environmental factors cannot be easily decoupled. So a big question we're working on right now is, can we quantify the present and anticipate future changes in human development under future climate drivers? And one of the things we've been doing is we are making an AI-based human footprint of the land surface. That is, we're using Landsat imagery, processing it through our, in this case, convolutional neural network, to predict this human footprint index at a very fine scale. So how much are humans interacting with the land? Now, there are many data sets like this out there. This is the one that's actually predominantly used in the ecological community. And so this value between 0 and 1, where 0 means it looks like humans have never touched it, to 1 you could imagine being a strip mall and a parking lot and everything in between. And because of this, we can now update it whenever we have Landsat imagery, which we constantly do. So this is the updated map from 2019. Now, I realize it's very hard to tell the difference of these two pictures, of course. But we can start to look at why did it predict differences in this human footprint index between 2000 and 2019. Here's one of my favorite examples from Sumatra. On the left is the year 2000. And it guessed the human footprint index was about 0.3. And in 2019, it said it doubled to 0.6. Then we can use explainable AI to say, why did you update that prediction? What was the network looking at to say it was a bigger number? And it really highlights this new Trans-Sumatran highway that had just gone in 2019, if you see that big red line. Furthermore, I've mentioned that XAI can help us with fine-tuning. So it's helping us gauge trust, but also during the process of setting up this network, we didn't know which Landsat channels would be most important. So we actually trained the network with many and used XAI to notice, in this case, that the channel on the left was more useful than the channel on the right for identifying these features. And thus, it allowed us to update our architecture and minimize our inputs. So we can look at differences between 2000 and 2019, and once again, use XAI to highlight why these changes are occurring. Actually, the example here, they're pretty small, I apologize, but the one in the bottom right, it says it's artisanal mining in Indonesia. This one was interesting. So my colleague here, Patrick Keys, spent like 100 hours looking at these over many, many days to make sure, because I trained the network, so I didn't trust it, right? Whoever builds the tool doesn't believe it. Isn't that how it goes? All right. And so he spent so many hours analyzing all of these outputs. And it looked like our network was getting this wrong because our labels, our truth, said nothing was there. So he ended up zooming in on Google Earth, looking, and he's like, something weird is happening, but I don't know what it is. And ended up having to use then Google Translate to look at a local newspaper to find out it was illegal artisanal mining that no one ever put down in the paperwork. And so the labels, the data we were training on, didn't know it existed. And so this is a case where this machine learning approach with Landsat imagery allowed us to see something that wasn't seen in the data set itself. And right now, we are updating this with far higher resolution and really trying to make a data set that's global for every year from 2000 all the way up till today. In order to try and understand how these climate hazards, like hurricanes and drought, have modified and changed sustainable development across the globe. So this is something we're working at right now. And let me tell you, if I hadn't used the types of tools being developed here today until this project, I definitely am now. This is big data, high resolution, and visualization tasks. All right. So in my final few minutes, I'm trying to tell you that explainable AI is really important for just nerding out on science, but also gauging trust in what we're doing. But even explainable AI has its problems. So this is where, and this gets into some vocabulary, and we can slice and dice it however you'd like. But many people in the community like to talk about interpretable AI. And this is a fantastic paper if you're interested in the topic, where Cynthia Rudin says, stop explaining black box machine learning models, which is what I've been telling you about up until now, and use interpretable models instead. That is, models that are built and designed to make sense every step of the way. If that doesn't make sense, think about something like a decision tree. You have a question and you answer yes, no, and it takes you on a new path, and then you answer yes, no on a new path. That's something you could put in front of a human and they could understand the process from start to finish, all right? So random forests, or at least decision trees, are a great example of interpretable. You make a big ensemble of those and we can talk about whether that's interpretable anymore or not. So Explainable AI tells us where the network is looking, but it doesn't tell us how it's using that information. And this is an example from that paper showing a heat map, like I showed you in the middle, of evidence or important regions for determining that this is a husky. And you're like, oh yeah, it's highlighting the husky, it's explainable, it makes sense. But then the right is the important regions for identifying whether it is a flute, okay? And it also looks at the husky. So this is not ideal. So something we've been doing in my group is working toward building AI models that mimic our scientific human reasoning to improve intrinsic interpretability. It's a lot of words, and I will say this is slow and hard. It takes a lot longer to train something that's interpretable to a human than it is to just throw it into the latest and greatest. But here's just as an example. This comes out of the computer science community. I read this paper and I said, I want to do this thing. They call it This Looks Like That, also with a title, pretty cool. This looks like that. And the idea is when you identify what kind of bird something is, how does your brain do it? Well, you look and you say, oh, I've seen that kind of head before. That reminds me of the head of this other bird I saw that once. Or I look at the feet and I say, oh, look at those feet. Those remind me of this other bird's feet I've seen before. In essence, we use these prototypical features to try to identify the bird. And that's just what they do. They build a network that has to learn prototype images to help it identify what kind of bird it is. Well, that's nice, but this should be titled, This Looks Like That Anywhere. That is, if a bird is upside down, it's still a bird. But if you put a hurricane in the southern hemisphere near Antarctica, it's certainly different than if you put it up next to Florida. So I can't tip my bird upside down. The location, if you will, matters. So what we did is, and this is, please be impressed, it's my favorite title ever. This looks like that there, okay? Thank you. I'm terrible at titles, but this one I will take credit for, okay? So we built an architecture that allows us to identify these prototypes, but they are prototypical pictures in a certain location. For example, this, on this image on the top, looks like that prototype on the bottom there in the middle of the Pacific Ocean. And what our network has to do is learn these prototypes and actually only learn n of them, which is specified by the user. So we constrain our network to only learn set prototypes for why it thinks something's going to happen. By constraining it, the hope is we are making it more interpretable to a human who then will go back and try to understand its decision-making process. All right, so to wrap up, there are lots of exciting things happening in this area, or even more generally for folks here using this sort of data. One big area, I thought I'd end with 3 that I think are really exciting that are, I don't see what's going to happen yet. So my crystal ball is still a little fuzzy. One is the role of AI in high-resolution Earth system modeling. It used to be in our field before machine learning came along that everything was always get to higher and higher and higher grid resolution. Because as we do that, we will be able to simulate those cloud processes, for example, better and better and better. With AI, one thing that's happening is people are saying maybe we can do that faster. But with higher resolution comes more data. And actually, one of the biggest discussions in these high-resolution modeling communities is how in the world are they going to save, process, and disseminate the amount of data they're talking about, all right? And one thing is I think we're going to see a lot of discussions of AI for data compression that the scientific community has been relatively against for a long time. Don't chop my data off. I already tried to convince you 10 to the minus 14 makes a big difference. So compression is a scary word, but I think we're going to have to embrace that in the future. Another big question is how climate change itself is influencing the data that we are training our AI models on. Now, I don't think we're going to train an AI model today and then in 30 years say, well, we trained it in 2024, we can't touch it again, right? We're going to keep training it with new data, but especially the fact that the last 40 years of heavy observations have seen large environmental and changes and trends. The idea that our data is stationary or there's a single relationship to learn is not the case. And so that's going to be a big question right now as to what extent what we're training today will be useful or whether the data we have today is the right data to train on. And finally, AI for weather and climate model replacement. This is a huge topic right now. Again, the idea of taking away the physics and merely having an AI-based emulator from start to finish of the pipeline. For weather, there is a lot of data to train on, and this is one of the reasons we've seen these AI weather models just explode in the last 2 years in their abilities to be on par with state-of-the-art from our community. However, climate, I will point out, is very different. People will say, oh, well, weather was easy, we can just do climate. Give me a year, we've got climate covered. I beg to differ, but they can prove me wrong. And the reason is the ocean. The ocean is slow. But the ocean, as I've already shown you, holds a lot of information about how the climate unfolds. Where are we going to find that kind of data for hundreds of thousands of years? It's not going to be observations. It's going to be climate models. And our climate models have their own issues. So I think instead we're going to finally see this reemergence of machine learning experts working with climate scientists together and data experts to try to map a path forward here. So with that, I'm done, and I will take questions. Thank you.
This was fantastic.
Okay,
I got rave reviews in real time as you were presenting things. Can I get this one too? Hello? Oh, awesome.
I'll stand far
Cool.
away.
Oh, thank you. All right, I'm going to start with one very meta question that I love. So this person says, I see a lot of growth in data centers and energy-hungry computing infrastructure. These are accruing towards being a sensible notch as a causal driver of global warming. Does that make climate scientists think twice about training large models? Is there an attitude of attempting to minimize computing usage in the field that does not really arise in other fields in comparison?
That's a great question. Yeah, so this is actually a question, believe it or not, that our communities had to deal with now for at least a decade. Because the climate models themselves, the dynamical climate models, are also huge in their energy consumption. So this has been something that has been talked about for a while, and actually some of the big labs report on their energy consumption to try to be open and transparent, especially because they're getting federal grants to do these things. This is absolutely something climate scientists talk about. I think when I have asked this question of some of the big leaders in the AI training model world, their response is the good we are doing for climate outweighs the emissions that we are setting off. That view is not held by all, but this is something that is absolutely being discussed and is relevant whether or not it's an AI model. So I don't have a yes or a no, but great.
Yes, that's not what I was expecting.
Yeah.
That's good. Thank you. How often do you encounter people who think AI means chatbot?
Yeah.
And how do you think, as someone who uses it to do serious stuff, can communicate this and dispelling that myth?
Yeah, so I think that the chatbot world is normally, you're sitting down for some holiday dinner with family is normally where I run into that. I think when I'm talking to people with a technical background or people interested in science, I actually tend to vie away from AI or even machine learning, and I call it nonlinear regression. And then they all go, oh, cool. And then they all open up. I mean, that's not going to work for my mom or my grandma, but so for those of you that have this issue, just call it, that's what I call it, and then everybody relaxes and you can have a really great conversation. So. Yeah.
Okay. Have you considered some therapy
Yeah,
training or
yeah,
something?
for sure.
Okay. Another question. Two people had the exact question at the same time. Wait, let me find it. How do you ensure that the climate model data used to train your model mimics reality and true climate data? Is there a concern that the model may be picking up on signals from the simulated data rather than what's in the real world?
Yes, this is what we spend at least 80% of our time worrying about. So first of all, actually, I can answer this yes or no. Yes, the machine learning algorithm is learning things from the simulated world that are not real. I can actually say that definitively. Because we've spent decades learning the issues, errors, biases within our climate model, we actually know and can list many of their faults right now for you because people have devoted their careers to trying to make them better. And that progress in some cases has been incredibly slow. That's one of the reasons that machine learning seems so exciting, is maybe we can jump one of those hurdles. But most of our time is spent exactly that, asking, just because it did well on the training data doesn't mean it's applicable to the real world. And if you had that mindset, then you might go, wow, the fact that it worked at all is pretty amazing. And that's my mindset every day. Whenever it works at all, I'm impressed. And so yes, that's really, really important. And I guess my message for all of you is know that, yes, we are aware of that, and it's what we spend our day in, day out doing.
Cool. Another question that I think you sort of hinted at an answer. I heard people say we should be more concerned about global weirding than global warming. Yeah. Okay. Have you seen explainable AI be useful for projecting or classifying global weirding? There were quotes around these words.
Yes,
I'm just the messenger.
So funny enough, that's actually my former life as a climate scientist, having major issues with that phrasing.
Okay.
So
tell us what we should say again.
Yes, no. So people think of climate weirding as oh, it could get really hot and really cold, and just things are going to be crazy. I don't love that. So let's back up instead. First of all, climate change and global warming is causing the globe to get hotter. But as I showed you, that doesn't mean it can't be cold sometimes, right? That doesn't mean it can't be really cold sometimes. But on average, it's causing it to get hotter. However, this idea of global weirding, I guess I'm going to be generous, is maybe instead saying, we can't tell you exactly what's going to happen, so prepare for a wider range of possibilities than you have experienced to date. And that, I think, is a great message, because we cannot make predictions for everybody's home in 5 years' time. I cannot tell you on your birthday it will rain a half an inch, right? That's never going to happen. And so instead, preparing from like an engineering perspective for things you haven't seen before is a great message. Yeah.
Thank you. One last one. How close are we to using explainable AI for weather/climate in operations or in the next IPCC climate report?
Ooh, great question. Depends on where you are. So I will say, at least in the federal side of things here in the US, that NOAA is a lot slower to incorporate things into their workflow. They're also very, very, very risk averse. And so that comes with, I'm not saying good or bad, but that's just how it is. We've seen, for example, in the EU, ECMWF, so their big weather, one of their big weather providers already has an AI model that they're using in operations already. And that happened in like a 6-month, this felt like a 6-month period. So I think machine learning first is going to be integrated into, say, the IPCC via model parameterizations, where they swap out tiny bits of the code for an AI-learned piece. Emulators as a whole, I think we're still a few years out, in large part because of that risk-averse mentality. But I guess my call here is, as those emulators come out, as those fully AI models are used, we need everybody that loves data to be looking at them, because we don't know their failure modes the way that we know the failure modes of the current models we use today. So.
Okay, yeah. I do have one more. This is just for me. Well, just for all of you. Do you have a call for everyone here of like tooling that you're missing, experiments you're doing, data? Maybe not data, but some people here actually may be able to provide you some data. But you have a call for help.
For this one, call for help. I'm going to have to think of that one. Instead, I'm going to change your question, though, and say
that's fine.
Thank
It's your
you.
show.
I was over at one of the tables collecting many stickers, and it was amazing how many stickers I recognized and was able to grab. Our community has to deal with so many different things, and you guys all are supporting that. I did not list all the tools that we use, but we use many, many, both visualization, the data side, the compute side, right? Just the number crunching side of inverting matrices and things like that. We're doing all of that every day. So thank you very much. That's how I'll end instead.
That's great.
Thank
That's
you.
even better.
Okay.
Thank you. That was
Thank you.
fantastic.
Thank you.